to our A. So this will be equal to 3/2 Vy over C squared, right? C squared minus Y squared. Then we are going to bring the C squared into the bracket. So 3/2A. Vy is outside. We're going to bring C squared into the equation or into the brackets. So now this will become 3/2A Vy 1 minus Y squared over C squared. Okay. So this equation over here that we just finally derived is exactly the same as this equation over here. Okay. So from here, what does this equation actually means? Okay. So by looking at this diagram over here, right, and we have derived the expression that the shear xy is equal to, now shear xy now is a function of y, because y is your variable, yes or no, right? So this is equal to 3/2A Vy 1 minus Y squared over C squared, right? So what we realize that when y is equal to, when y is equal to 0. Okay, so when y is equal to 0, okay, which is at the global centroid position, right? So if this at this point over here, remember we say that this is our datum, right? So when y is equal to 0, what we have is the shear xy will become its maximum. So because this is 3/2A, right? Vy bracket 1 minus 0 over C squared. Okay. So this will be equal to 3/2A Vy. Okay. So the maximum shear will occur at the datum, and this is only true if the entire thickness, you can see the thickness is constant. Okay, the entire thickness is constant. And what we realize when y is equal to c, okay, y is equal to c, which is the distance furthest away from the global centroid position, okay, the shear xy will be equal to 0 because you have 3/2A, right? Vy 1 minus by 1 minus by C squared over C squared, right? So this is also equal to 1. So this will be equal to 0. Okay. And if you were to look at the global, the parent function, right, is this expression over here is a second order polynomial equation, right? So when you come to this, when that's the case, you can sketch out the distribution. Okay, we're going to sketch out the distribution now. Okay. So if we were to sketch out the distribution, this will be our shear stress, xy, and then this will be our distance, y. So this is 0. What you get with a second order polynomial function and it's negative, you get a set phase distribution. Okay, and then this will be reflected on the other side. So I'm going to flip this across. What is happening? Let me escape. Sorry about that. Okay, so this is how the distribution will look like. And you will realize at this position, this is the location of the centroid, right? The global centroid. You have tau max at the global centroid, and furthest away, your shear is equal to 0. Okay, and this will comply to the formula that the shear stress is equal to, or shear xy is equal to 3 over 2a bracket 1 minus c squared, or 1 minus y squared over by c squared. Okay. Now, a very interesting feature that you see now, okay, if we have our, I'll draw another diagram over here. Okay. So we are still going to comply to Vy is in this direction. And if we were to draw or sketch in terms of normal stress, so this is our Y and this is our normal stress in the X direction. And if we were to use this formula, hey, my over Iyy, I got this mixed up, multiplied by Z. Okay, so when that's the case, right, it's just an example. I want you to look at something. Okay, so let's say we have a distribution that looks this way now. Okay, so we know that this is our centroid. So the big thing that I want you all to see is for shearing stress, right? The maximum is at the what? Centroid. For bending moment, our maximum stress, so in terms of compression, is furthest away from the what? Centroid. Okay. Later on, we have to combine these two together: normal stress and shear stresses. Okay. So that's where we have to be really careful with the distribution trend. Okay. So the question is, where do you pick? Is it you use the maximum normal stress, maximum calculate normal stress, or your shear stress? Depend on your loading condition. Okay, that's all I can tell you for now. Right. Next, we are going to look at another example. Okay, we are going to do an actual calculation now, and this will be our example number 1. Okay, so the example you can find over here. Okay, These are all on Avenue to Learn, okay? And this is a very good learning example. Okay, let's look at this. So what we have over here is for the beam and loading condition shown, consider section NN and determine the stresses at point A at point B. Okay, so what I'll do now, we will go for a 5-minute short break, and then we come back